and fusion. This is where we get our atomic bombs from. Okay? Fission is when we split a large atom into two or more smaller atoms, and that just goes with the name of fission. A fissure is a crack in something. So fission is breaking apart a larger molecule into two or more smaller molecules. Fusion is where we bring two or more smaller particles and we make a larger one. In order for fission to happen, the parent element has to have a critical mass and a high-speed neutron. It doesn't require a whole lot of energy to split atoms in a fission reaction. Okay? They're happy to break apart. Fusion is very high dense and high temperature environment required. This fusion requires a lot of energy. High density required, so high probability small particles will collide and fuse together. High energy is required to bring these particles close enough together that they overcome the electrostatic repulsion. So going all the way back to fields and forces in the very first couple sets of notes, when we looked at electrostatic repulsion and we looked at rubbing balloons on our hair and the transfer of electrons and how that worked. Okay? When we're looking at particles that are like this part here, where we're talking about overcoming the electrostatic repulsion, this is the London dispersion force that we learned at in bonding energy. It needs to overcome that. Energy released. Energy released by fission is 1,000,000 times that greater than what a chemical reaction can do. But it's lower than the energy released by nuclear fusion. So here's kind of the ironic thing. Nuclear fusion requires a phenomenal amount of energy to happen. But when energy is released from fusion, it's 3 or 4 times greater than fission. So if fission is 1,000,000 times, now we're 3-4 million times greater than that. The return output of energy is far greater than the amount of energy required. So that's why they look at fusion as being a source of energy, even though it requires a natural amount of energy. Fission doesn't normally occur. It's man-made, and it's for the atomic bombs and nuclear power plants. Fusion does occur. That's where we get our stars from, and that's where the thought is we get our sun from, at the core of our solar system, is through a reaction that brought two or more particles together. And what we're experiencing billions of years later is still the energy given off of that reaction. That's our Big Bang theory. Byproducts of the reaction, fission gives you lots of highly radioactive particles. It's super harmful. Whereas in fusion, because you're bringing small particles together to make one bigger one, there's less radioactive particles, and so it's not harmful. In a sense, we can still be harmed by our sun. But just to be outside when the sun's outside is relatively safe. To be outside when an atomic bomb goes off is not safe at all. Okay? So again, there's going to be 1 or 2 questions based on this chart. This is the piece that we need to know. And this picture, unfortunately, photocopied from a textbook, isn't the easiest to see. So what we have in fission, remember fission is the splitting of a larger molecule into smaller ones. So we have a neutron that will come and react with uranium. And so uranium then will split into smaller daughter cells, and you will get strontium, and you will get xenon, and you will get 3 more neutrons. So you can see where I put a little bit of energy in with the neutron. I'm going to get 3 neutrons out of it. When you look at fusion, so deuterium, remember I told you it's called heavy water. So deuterium is that H2 over 1 molecule, and another smaller particle called a tritium, which again is hydrogen 3 over 1. When they combine together, you produce a neutron, you produce a helium 4 ion, and this release of energy. And this release of energy is 3 or 4 times this release of energy. Okay? And that's what you need to understand about fission and fusion. It's a concept question on the diploma. So for example, explain why only relatively small nuclei can undergo fusion. And it's because they have less protons, there's less electrostatic repulsion, and then with the less electrostatic repulsion, they can fuse together rather than being broken apart. And those you can look at questions 1 to 3 if you like. Let's look at, I don't even have practice problems for them. That is the practice problem 1. So it's just a concept question. Okay, so that is fission and fusion.